Good morning. So once again, welcome to the control systems class. So last class you are seeing that modeling of physical systems. So that is two types, mainly translation systems and rotational systems, and then also learn about the problems in translations and rotational systems. Now coming to the next topic, electrical systems, right? So these are one simple technique to can find out the transfer function by applying the Laplace transform, similar to the previous cases, that is the translation systems and rotational systems, right? So now we take the electrical systems. You are taking here resistor, inductor, capacitors. These are the three basic elements of the electrical system. I think already you know very well, right? So that the behavior of any systems is governed by the Ohm's law, right? So which elements you append? Inductor, capacitor, resistor. Now consider first resistor. Okay, consider the resistor. So resistor, whenever given the supply, that is apply the voltage, so current will flow, right? So taking here the current, voltage and resistance, right? Now considering the resistor, so here voltage applied to the resistor is equal to I into R. Actually the voltage, what is Ohm's law? The voltage applied across the resistor is proportional to the current, right? So V equal to IR. So IR is the proportional constant here. So that is called as resistance here. Now resistance. Now we're taking the one resistance, you are applying the voltage, right? So voltage V, right? So you are getting the current through the resistor. So V equal to I into R or R into A, right? Now suppose there is two currents carrying, that is maybe in two sides. Okay, sometimes you can observe in a closed circuit or network there are two currents will flow at a time in a resistor. So in that case, what you are taking, so V equal to difference of the two currents into multiplication of the resistance, right? So you are taking the I1 minus I2 into R. So depends upon the direction, it may be I2 or I1 minus I2 or I2 minus I1, right? Now coming to the inductor, so L, so inductor is the storage element, stores the energy or power, right? So V equal, what is relationship voltage and current in the inductor? V equal to L di by dt, or I equal to 1 by L integral V dt, right? So these are the two basic elements of the resistance. So next one is the inductor. Same previous case you have seen about the resistor. So you consider the two currents. So you are taking the V equal to I1 minus I2 into R. Similarly, in this case also inductor also you are taking the V equal to L di 1 minus I2 d by dt. Okay. So coming to the current, so I1 minus I2 equal to 1 by L integral V dt. So these are the basic equations you must be keep it in mind and remember, right? So as a electrical students, you must be know the basic equations of the basic elements, right? Now consider the capacitor. So capacitor is the energy storing element. So what is the relation in capacitor voltage current? V equal to 1 by C integral I dt, right? Next I equal to C dV by dt. When you consider the single volt, that is only one voltage and one current, that is only current, then V equal to 1 by C integral I dt, then I equal to VC dV by dt. Now if we to take the two currents, so I1 and I2. Now in this case we are taking the 1 by C equal to I1 integration of I1 minus I2. Similarly I equal to, that is I, the difference between I1 is C dV dt. So these are the basic elements you are using in this electrical systems and their equations. Now consider the simple RLC circuit. So RLC connected in series, right? So applying the Z E of t are taken, then output was V naught t. Now find out the transfer function of this electrical circuit, that is the output voltage by input one, right? So the Laplace transform the output by Laplace transform the input. Now this is the RLC circuit are taken. So just simply, so already as a electrical students you know, but the as per the Kirchhoff law, the applied voltage is equal to voltage drops in the elements. Okay, so applied voltage V E of t equal to the voltage drop in each element. So already you have seen the previous slide. So the voltage and current relationship inductor is equal to, we are taking the voltage here. So depends upon the equations, the internal equation will change. You are now considering voltage here, the applied voltage E of t. So take the only voltage equation inductor only, right? So V equal to L d by dt. Then I equal to in resistor, V equal to I into R. In inductor 1 by S integral I dt. Okay, the same equation now substitute in voltage balance equation. Okay, so applied voltage equal to voltage drop in each element. Okay, so L di by dt R into I 1 by C integral I dt. Right, now apply the Laplace transform through this equation. So E of S equal to, so already I told in the previous class, when I apply Laplace transform, when it is d by dt, the S will come, when d square by dt square will equal S square will come. So like that you will get the Laplace transform d by dt in d by dt. Okay, in place of d by dt you can get the S. It may be square, cube, or 4 times 3 times. Okay, so now E of S equal to Ls into I of S, R into I of S, then 1 by C of S into I of S. Right, then assume the initial condition 0. Now taking the I of S as it is a variable, the common, so I am taking the I of S as common. Okay, so I of S in term in each case, I am taking the I of S common. Then take the, when you take Ls R 1 by Cs. Now I am taking the LCM to 3 terms. I am taking the Cs as a LCM. So when CS not there, so CS LCS, that LS into CS. Now equal to LC is S square plus R into CS. So RCS. So plus S1 additive. So this is I of S. Okay. Now let them take, so in a capacitor we are taking the Laplace transform. We have 1 by CS by I of S. Okay. So that is, we are taken only input. This is input voltage equation. Now I am taking the output voltage. But coming to the CS. So this is the voltage across the capacitor. So what is the voltage across capacitor? So previously we are written voltage equation V equal to 1 by integral I dt. So the voltage across the capacitor. So the applied voltage equal to voltage drop in each element. That is the another one equation. The other equation is taking the output voltage. The output varies appear only across the capacitor only. So that's why the output voltage equal to V naught of S equal 1 by integral I dt. Now apply the Laplace transform. So V naught of S 1 by CS into I. So in this case, so actually what you want output voltage divided by input voltage. So I eliminate the I of S. So from this equation, what is I of S? Now substitute in this case. Okay. So G of S will be V0 by I of S. Okay. Now 1 by CS equal to. So in place of CS, we take the I of S. So in I of S here. So 1 by CS. Understood? So here I of S. So what is I of S if we take this side? So what is I of S in this case? We will get here. So I of S equal to I of S, take the same. So into this side. So it's I of S by remained 1 plus RCS plus LCS square. Same thing you are written here. Okay, right? Now, so after eliminating the I of S and I of S cancelled, you will get the same thing. Right? We can substitute in this case also. Right? So you will get the V naught of S, V of S equal to this one. Right? So C of S, C of S will cancel. So C of S will cancel. Okay. So this C of S, this C of S cancel. So automatically this I of cancel. So we will get 1 by LC square by RCS plus 1. Okay, so this is the simple equation for electrical systems, right? So you get the similarly I am taking the one network. Okay, so R1, C1, R2, C2. Okay, now for this also write the loop equations. So how many loops are there here? In this case 2 loops are there. So this is the output voltage across the CS2. Now apply the loop analysis, right? So simply applying the 2 loops in there. Okay. So here in the first case there is a voltage apprentice there, but you are not applying any voltage. So that's why I am taking here. That's why I am taking the here 0. So apply voltage 0. Okay, right? Now the in the input side is only Vi of S. So Vi of S, right? Plus the so this one, so I of S. So what in current, then is R1. So in R1, write the voltage balance equation, right? So in this R1, so voltage into I of S. Similarly, in this one also 1 by S into C1. Similarly, okay, write the loop equations. Loop analysis, I think you know very well. Okay, so 0, so we input voltage, then 1 by SC1 I2, then 1 by SC1 I1, right, minus I1. So that is taking the here. So I am taking the I1 is common, because I1 is common, then I2. So I am separating I1, I2 terms, right? So we take the I of this side. Okay, simply apply the, so whatever the studied in loop analysis, you apply the loop current analysis. Okay, then we will get this equation. Then similarly for second loop also same thing. Sorry. Sorry. Now for second loop they also apply the second loop analysis, loop equation. Right? Second loop. So you can observe here there is no voltage in this one. There is no supplied voltage. That's why I taking here 0. Right? 0. Now I have similar previous to case also similarly apply the loop analysis. So I1 into what is here. So here because this I1 minus I2 into 1 by SC1. Then here R2 into I2S. Then here also 1 by C2 into I2S. So you can observe same voltage equation, right? So I1 1 by C1, I2 1 by C2. Because these two, because this element, the what is the element? The 1 by SC1 is between the I1 and I2. So that's why I taking here. Actually, what we will written here 1 by SC1 into I2 of S minus I1 of S, right? Plus I2 of S into R2. Okay. Similarly, in this one also we will take it. In this one multiplication we will get plus 1 by S C2 into I2 of S. Same equation. So same equation in this one. Okay. Observe it. Okay. Same equation. Right. So now separating the I1 terms and I2 terms. This is the one equation. Okay. So from equation 2 we are taking the one I2 that I1 SC1. Okay, so from these two equations I have to separate the either I1 or I2. Okay, so actually what is the equation of the output equation is you take the in terms of the V1 of S by, that is output voltage divided by input voltage, that is the transfer function. Okay, now eliminating the either I1 or I2. Now I am eliminating the one I1. Okay, so substituting 3 in 1. Okay, I1 wherever I1, okay, I am substituting. So you will only turn up I2. Okay, I want only I2 terms. You have to eliminate. We are seen in previous classes, that is you are eliminating either x1 or x2 or y1 y2. Okay, similarly here also you are eliminating either I1 or I2. So I am eliminating the I1. I am keeping the all the I2 terms only in this equation, right? By substituting. Okay. Now I will take the V1 Vi into obviously equal to I2. Okay, the same equation. Now I am finding the output by input equation, because the output, what is the output equation? The output equation is observe. What is the output equation? So only V0. So V0 of S equal to what will come here? So V0 of S equal to 1 by S C2 into I2 of S. Right? 1 by C2 into I2 of S. Here on. Okay. So you can observe here. What is the output equation? You can see. Yes, this you can observe. Okay, V0 of S equal to I2 into 1 by C2. So in this case, I2 equal to this one. So I2 equal to S into C2 V0 f. So previous case we are given only I2 terms here. Okay, so you can observe only all are I2 terms. You are eliminated I1 term. Okay, so input voltage equal to I2 into. Okay, now in place of I2 you have to substitute the extension. So in place of I2 you are substituting S into C2 into V0 of S. So of substituting, then you will get the output, that is the output divided by input. That is Laplace transfer output divided by Laplace on the input put. Okay, now we take the this one. Now, okay, this side. Or it may be taken other side. So cancel the sum terms, and then you will get the transfer function of the V0 of S by Vi of S. Right? Clear? So we must be right. We must be in Laplace transfer. What is transfer function? Laplace transfer output, Laplace on the input. Okay. So while doing the calculations or equations, you must be think about the which term will eliminate really easily, because here the output, you can observe the output voltage is in terms of S 1 by S into I2. So if you keep all the terms in terms of only I2, okay, eliminate the I1, first equation and second equation. Okay, then you will get the simply you will get the output voltage by input voltage, right? So this is the one of the example for the electrical systems, right? Now we go to the electrical analogous and mechanical resonance systems. What is analogous? So systems remain analogous as long as different equations governing the system or transfer function, so are identical form. Okay, so the electrical analog of any kind of the system are very important, since it is easier to construct the electrical model analysis system. And that is, if you give the mechanical systems, so how to convert to the electrical systems, right? That is called analogous. So what are the basic elements in mechanical system? Mass, dashpot, and spring. What are the basic elements in electrical systems? Okay, what are the elements of resistance, inductance, capacitance? Okay, you have to replace that with a. So there you are getting the what you are there force you are getting in a translation system, either force or torque. Okay, in electrical system it may be either voltage or current, right? So the output well, right there you can change. So there are two analysis systems here. One is the force, that is the force voltage, and force current for translation system. Similarly the other for a rotation system also is there. So for rotation torque will come, right? Torque, similar torque. Okay, so either force and torque in translation system will get the force, and rotation system will get torque, right? So we are convert to the systems electrical system. So in this case, what will get here? Force current, force voltage. Similarly, torque current, torque voltage, right? So in a translation systems, the electrical system will get the force voltage, force current, right? In rotation systems you will get the force, torque, and torque current and torque voltage, right? So these are the two analyses there in this system. Now we can go to the force voltage analogy. Okay, so force voltage, then this is the balance equation. So you can see there. So in a mechanical system, so already you are seen mass, dash part, and spring, right? So in this case, the dash part, okay, you can see the dash part, okay, dash part. So you are taking same similar to x. X means displacement, v is velocity. Okay, so velocity is the rate of change of displacement, right? Acceleration is the rate of change of the velocity, right? To keep it in mind, right? So then what is equivalent to the dash part in electrical system is resistor. Okay, the mass, that is the mass in mechanical systems, is equivalent to the inductor. So actually it is inductor. It is a printing mistake in textbook. So it is inductor, right? So in a mechanical system, the mass, it is equivalent to the which element is equivalent to the electrical system? Inductor. Similarly, the spring constant you are taking in mechanical system equivalent to the capacitor. Including capacitor in electrical systems, right? So the equation is the same, no change. Now we are taking, you can observe here, right? So in terms of the displacement, F equal to, actually what is the force equal to mass into acceleration. Now we are taking the displacement in this case. So that's why m and d square x by dt square. If we consider the velocity, m dv by dt. Clear? M dv by dt. Similarly, here we will get the E equal to L dv by dt. Okay, the voltage V equal to, in place of V, voltage you are taking the E, EMF E. Okay, we can take V also, no problem. Okay, so V into L dv by dt, right? Similarly, here the dash part B equal to, so force is equal to B into dx by dt in mechanical system, or BV. Similarly here, so E equal to I into R, or R into E. Okay, similarly coming to the spring constant, so F equal to Kx, okay, or integral V dt. Okay, similarly you take the here E equal to 1 by C integral I dt, right? So these are the basic elements compared to the mechanical system and electrical system. There are two analogies, force voltage and force current. Now we are considering only force voltage. Okay, so you can observe force voltage, are taking the voltage, right? Voltage. So in this case, dash part equal to the resistor, mass equal to the inductor, and spring is equal to the capacitor. So this is the difference. These are the force voltage analogy. Now come. So then the item are taken, that is a simple table. You are comparing the terminology in a mechanical systems and electrical systems. So what are the terms is there in the two systems? Okay, so here independent variables input and output. So here force is you are applying the force. You have already seen you are applying the force in translation system. What in this case of electrical system, it is voltage. Okay, in this case velocity, here is the current. Okay, here for frictional coefficient, that is equal to resistance, then mass equivalent to the inductance, then spring constant equal to inverse of the capacity, inverse of the capacitance 1 by C, inverse of the capacitance 1 by C. You are applying here Newton's second law, here applying the KVL. Okay, so the algebraic sum of the force is equal to 0, and then here algebraic sum of the voltage is equal to 0. Right, so here lever, take the lever F2 by A1 or L1 by L2. Here similarly lever the N2 by N1 by N2 or E1 by E2. Okay, so these are the just some comparative table between the mechanical systems and electrical systems. Okay, by seeing this table, you can clearly observe and keep it in mind. So it easily remember also, it is okay, very easily remember. So here force, voltage, velocity, current, frictional coefficient, in dash part is resistance, then here mass, inductance, then spring constant, inverse of the capacitance. So which law you are applying here? Newton's second law. Which law you are applying? KVL. So here the algebraic sum of the force is equal to 0, algebraic sum of the voltage is equal to 0, right? So these are the comparison table between the mechanical system and electrical system in force voltage analogy. Right. So similar to the previous, already you are seen in translation systems and rotational systems some few points. So how we write the equations. Okay. Similarly, there are also some few points. So in electrical system, the elements which are in series will have same current. Already you know this very well in circuits. When there are series circuits, which element is common, current is common. Right, likewise the mechanical systems also. Okay, mechanical system same velocity is common in series. Right, similarly here having velocity in mechanical system have the same current in electrical analog systems. Right, so each node mechanical system correspond to the closed loop in electrical system, and each node in mechanical system correspond to closed loop in electrical system. Okay, say mass considered be node here. Here you are using the mass as a node. Right. The number of meshes in electrical analog same as the number of nodes in mechanical systems. Okay, then here the number of mesh current systems equation will be same as that of number of velocity of nodes in mechanical systems. Okay, that is number of masses equal number of loops. Suppose there in a problem there are two masses. Okay, two masses. Then you can get the two loops in the electrical systems. Okay, then mechanical driving systems and passive elements connected to the node. Right, in mechanical systems will represent closed loop in electrical analog system. So the element connected between the two masses in mechanical systems, separate common element between the two meshes in electrical system. Okay, these are the simple points we can remember while doing the problems. Right, now we can observe. So previous table as already we have seen. So which parameters is equivalent to mechanical and electrical systems. Right, now you can see the how to draw the similar, that is mechanical system and electrical system. Now you can observe here the dash part. Now you can electrical system. Okay, so the mass you are taking the voltage. So previous case you are taking force voltage analogy. Now you get the force current analogy. You can observe here. So previous case dash bar is equal to resistance, same, no change. Okay, you can observe force voltage analogy. See, force voltage analogy, and the whatever you are taking, the dash part is resistor. Okay, you can observe force voltage and the dash part equal to resistor. Same way in force current analogy, dash part equal to resistor. There is no change. Only the change in the next two cases. Okay, so here mass equivalent to the capacitor. Previous case mass equivalent to the inductor in force voltage analogy. Okay, so in this case the spring constant equal to the inductor. So previous case force voltage analogy, the spring constant equal to the capacitor. So these are two are interchanged in previous case. That is force voltage, force current. What is the similarity in force voltage, force current? The dash was equal to the inductor. That is the resistance. So that is the difference. So when you see, when you compare the previous case, next case, you can easily remember. That is the only thing, right? Now similar to the force voltage analogy, then you are taking the same table comes here. So there you are taking the force, in this case current. So previous case is voltage. Now in the case velocity, previous case, now in this case there is the force current velocity voltage. Previous case these are two interchanged. Okay, then friction coefficient is conductance. Okay, 1 by r. See, mass equal to capacitance. Then stiffness, this is the inverse of the inductance. So only the change is here. So you can observe here 1 by r. There r. In previous case force voltage analogy, it is r. Now it is 1 by r. No, then and also stiffness of spring, previous case, that is force voltage analogy, it is the 1 by c. Now it is the 1 by l here. Okay, so same Newton's second law. There you are taking the KVL. Now here KCL. The larger that force is equal to 0 is all the current is equal to 0. That is the only change. So because F1 by F2, I1 by I2, same L1 by L2, N1 by N2. Okay, the same. Only the difference. So in this case, right? Then. Now the same previous case, whatever the guidelines are there, similar here also. So electrical system elements which are in parallel. See, there this in force voltage is series. Okay, in series currents are same, but it is parallel. So same voltage. The only difference is can observe here. It is parallel. In previous case, the force voltage is series. Same currents there. Here same voltage. Okay. So like mechanical system, the elements having same velocity, mechanical system have analogous to the voltage in electric system. then each mass in mechanical corresponds to the node of electrical system, same as the previous case. The number of node voltage systems will be equal to same as the number of velocities. Then mechanical driving sources and passive elements connected to the node in mechanical system should be represented in analogous connected to a node in electrical systems. Okay, then electrical connected between two nodes, right? The mechanical system represented in common element in two nodes. Okay, right? So here force voltage, you can see the node force voltage analogy, you are using the KVL. In force current you are applying the KCL. So current KCL, that voltage KVL, right? Now I'm taking a simple example, right? Now write the as usual, write the balance equations, then convert to the two another. So here asking the draw the force voltage and force current electrical analogous with the and verify with the node equations. Okay, now how many masses are there now here? Two masses are there. Okay, you can see the previous case you are applying only x1 x2. Now you can observe here v1 v2, right? Now here we are applying the force here, then there is a friction coefficient b1 b12 b2, then one spring constant k1, other spring constant k2 is there, one side is fixed, right? Now apply the similar whatever you are studying in translation systems, the same equation one. So draw the free body diagram, right? So you can observe the force. Where is force now? Now force here. I'm taking the M1. Okay, force, right? So inertia, because of inertia, same inertia. Okay, right? Because of inertia, there is the F M1. Okay, actually this force you can apply here. Where is the force now? In this direction. Oh, same direction. Right. So this is the force. Right. Now apply the free body diagram. Apply the Newton's second law. So F M1 one weight, then F B1. Then Fb12, then Fk1 equal to applied voltage, then applied force, right? So because of one inertia, one weight of the mass, so m1 d square x1 by dt square, and you are writing in place of displacement equations, right? Then b1 dx1 by dt, then b12 d by dt x1 minus x2. You can observe where it is between the two. So b1 is between the two displacements, x1 and x2, right? Then between the two displacements. Right. No x minus x2. Similarly the k1, that is spring constant also between the two, can see between the two elements, between the two displacements k1, right? So that's why you get the k1 minus x2 f of t, right? Now writing the same similar equation for the second. So same, can you observe? Right, same for m2 also I'm writing here. For m2 also m2 dx1 dt, b2 dx2 by dt, k2 x2, b1 to d1 by x2 minus x1, k1 to x2 minus equal to 0. So for mass 2, okay, for mass 2 for this one mass 2. So one side fixed now. So that's why k2 into x2, b2 into b2 into dx2 by dt. Now m2, okay. So when m2, so m2 is one weight. Okay, so one weight will come with, so m2 into dx square by dt square, right? So these are equals for second one. So equal to 0, right? So I'm taking the, now apply the, now you are taking the force voltage and different equations, force voltage, right? So you are just equating the also. So d square x by d square dv by dt, right? dx by dt is equal to v, then x equal to integral v dt. Now applying to this one. Now take the m v1 dv1 by dt, now changing. So you can observe here m dv1, so previous case this one, right? So d square x1 dt square, in place of d square value you have to write here d square we are writing the v1, d square x we have write dv by dt, dx by dt we are taking v. So in place of x integral v dt, same applying the previous equation for this equation. He is d square replacing the dv by dt, right? dv by dt, right? dv1 by dt. So b1 b12 v1 minus v2, right? So what is b12 into b1 to d by dt x1 minus x2, d by dx1 by dt, what is there? dx1 by dt dx1 by dt, so v1, right? So v2, right? So v1 minus v2. Similarly k1, so in place of x, right? In place of x, so in place of this one x, so x1 x2, in place of x what you will get here, in place of x In place of x, what will get? 1 by integral v dt. So integral v2 minus v. Okay. So previous case v1 minus v2. Right? Right? Now get the equations. So after writing the in terms of the dx by dt in with dv by dt, dx by dt with v, x equal integral dt. So you are replacing the terms. That's all. Nothing you are doing here. Just you are replacing the, in place of x2 you are replacing with the v, because it is a force voltage analogy. In place of displacement you are applying the voltage. Right? Just replacing the equation, replacing the terms. Right? So m2 dv by dt, b2 v2 plus k2 integral v2 dt, b1 to v2 minus v1 plus k1 v2 minus v1 to dt equal to 0. So the first equation is the second equation. Right? Now apply the force voltage analysis circuit. Now you have to draw the circuit. Right? So in this case, force voltage analogy, force equal to the EMF, excitation EMF. M1 equal to the L1, B1 equal to the R1. Okay, already you are seen in table. Okay, so spin constant equal to inverse of the C1. Right? X1 equal to I1, M2 equal to L2, B2 equal to R2, K2 equal to 1 by C2. So B1 equal to R12, X2 equal to I2. Right? Now replacing the equation. Right? Now you can observe. Now I will this is the circuit of the force voltage analogy. Right? Force voltage analogy. Right? Force voltage. So how many sources are there here? M1, M2. So there are two masses. So we'll get two loops. How many loops you can observe here? Two loops. Right? Two loops are there. So these are the M1, M2. Right? So M1. So M1 is connected to force. Right? Then M1 connected to the K1 and B12. One side. Okay. So you can observe here. So force is happening EFT. Right? So M1 connect to the K1 element. So what is K1? K1 R1. Right? L1. B1 to L1. Right? Now between the M1 and M2, what are the elements are there? Between M1 and M2, K1, B12 is there. Okay, K1, B12. Right? Then other side, what are there? K2 and B2. Understood? So the same thing can get here. C. So R1 to C1. So L to R2, then C2. Right? So in terms of mass. Okay. Clear? If you want, I will go back. You can see the element, each element is equal to other. See. Yeah. See. The dashpot equal to the resistor, mass equal to the inductor, then spin constant to the capacitor. Right? So here you are taking the M1, M2 as a two loops. So M1, M2 as two loops. So for this M1, M2, which elements are connected? Right? Clear? So in place of M1, you are writing the C. So capacitors. Right? So I1. So they are taking the X1, X2. So I1, I2. In place of X1, I1. In place of X2, I2. Okay. So you are taking the R1, L1 and R1. Similarly, L2, R2. So between the M1 and M2, what are the elements are there? R1 to C1. Right? R1, C1. Okay. So R1 is a spring constant. Right? R1 is a spring constant. C1 is the dash part. Right? Connected in series. And these two in parallel. So these series, for this one, these two in series. Right? So simple. Very, very simple. Right? See. So for a mass capacitor, right? You can observe there are two masses. So where the capacitors are connected, see capacitors, right? Two capacitors, M1, M2, right? But these M1 and M2, which are between M1 and M2, which elements are there? Just to observe which elements are there? K1, B12. See between the two, C1, B12. So B1 to R12. Right? So dash material C1. Right? Clear? So these are the individual elements for these two masses. These are the common elements between the two elements. Right? These are the individual elements for each mass. right? These are the two are common between the mass 1 and mass 2. Clear? So very easy to draw the circuit for force voltage. So which is common here? So voltage is the parallel circuit. So force voltage common in parallel, right? See, right? Now coming to the next case. So force current analogy. So force current mass equal to C1. So force current I. So what is previous case you can observe? F of t equal to V of t. Right? X of 1 equal to I1. X of 2 equal to. But in this case, X1 equal to V1, X2 equal to V2. Clear? So M1 equal to C1. Previous case M1 equal to L1. Clear? So 1 by C1. So M2 C2. So B1 1 by R1, B2 1 by 2. So K1 1 by L2, K2 1 by L2. So right now you can draw the equation, right? So between, so you can observe there you are connected in series and the parallel. Now here you can observe all are parallel or two series. Which one is series? L1 1 by N. So what is right? So these two, what these two you can observe the case. These are no these two K1 B1 2. Okay, K1 or resistance will come in place of B1. So you can observe, right? Sorry, next slide. See, K1 means, right? You can observe 1 by R L12. B12 means L1 parallel. Now for current, you are taking the here parallel. So current. So these are for mass M1, these two common. For mass M2, these two common. So taking the two nodes. So we are taking the V1. So see, in force voltage analogy, you are taking the two loops. In force current analogy, two nodes. Okay, you can observe the two nodes here. Two nodes V1 and V2. Between the two nodes, what are they? Two elements are there, spring constant and dashpot. So it replaced with the resistor and inductor. These are the individual elements, C1, R1. Next, these two, C1 there. So 1 by R2, 1 by L1. Right? These are the mass. Right? So here, there you will get the series with parallel. Here, parallel with series. Okay, so you can observe the circuits difference. So series, parallel. Here, the common elements between M1 and M2 will come in between the two elements, right? And next for force current analogy, you can observe coming in series. Clear? So these two in series. Previous case, these two in parallel. Individual resistor capacitor, individual resistor capacitor in parallel. And previous case, it is the series. Okay, right? So 1 by R1 to L1, right? There two loops, the two nodes here. Clear? So these are the simple convert mechanical systems to electrical systems, right? Now write the equations, previous equations. So I'll apply the KCL, right? Apply the KCL, write the equations, right? For node 1 and node 2, for node 1. So all the incoming currents or outgoing currents are equal, okay, right? So incoming current, this one, right? So applied current, C of t equal to remaining all are same. So what is there here? C1 dV1 by 2, here 1 by R V1, right? See here 1 by R1 into, because between two nodes V1 minus V2. Similarly 1 by L1 into integral V1, because inductor V1 minus V2, right? Then coming to this node, writing the equation for each node. This node coming to each node, this node. So single element connected, so C2 dV by dt. Similarly this for this element 1 by R2 into V2, for this element 1 by L1 into V2. Then between the two elements V2 minus V1, what is the 1 by R1 to V2 minus V1. See, V2 minus V1. Previous case is V1 minus V2. Now in this case, then similarly 1 by L1 into V2 minus V1. So there is no voltage here. See, for this node there is no voltage source, only for is the current. Here only current, incoming current. For this one and so that's why I taking here 0. Okay, so this is incoming current. For this node there is no incoming current. Okay, right? So that's why we will get for first equation we will get I of t equal to remaining the KCL. All the sum of the currents equal to 0. This one, right? Applying the equation. So these are the these are the simple example for force, voltage, force, current for translation systems. Translation systems. So translation system, what you are getting here? Force, mass, then mass dash part and spring constant 3, and connect taking the force voltage, force current. Similarly for rotation systems also. Okay, rotation system, what you will get here? Rotation system, moment of inertia and rotational dash part. Okay, then rotational spring constant. Here also will get the, here in place of force you will get here torque will get. Okay, only the thing torque, but the same force, there you are taking the force voltage, you will get the torque voltage. There you are getting the force current analogy, you will get here torque current analogy. Okay, the common term voltage and current, only the change, there you are getting the force voltage, here you are getting the torque current. So rotational systems you will get here. Okay, in rotational systems the elements may be moment of inertia, rotational dashpot, and torsional spring will get here. Okay, see you can, right? So torque voltage analogy. So the guidelines is similar to the previous case, same electric systems which are series in same as current, okay, like a mechanical systems. Then angular velocity mechanical system same as the current in electrical systems. Then closed loop electric system same as in considered as a node. Okay, then number of meshes in electrical analysis system same as number of nodes in mechanical systems. Then the number of mesh currents equal to the angular velocity node systems. Then the mechanical driving source is equal to passive elements connected to the node in mechanical systems. Then you will represent with the closed loop, right? Then the elements between the two nodes in mechanical system with the common element in the two meshes. Okay, now you can see the one table also. So you can observe the previous case, mechanical systems, electrical systems in previous case also. Okay, mechanical for translation systems you will get the torque there, translation will get the force, in rotation system you will torque here. Here voltage same. Okay, angular velocity, current, then rotational coefficient of dash part same as resistance, moment of inertia, so inductance, then spring constant, that is inverse of the capacitance. In Newton's second law, Newton KVL, these are no change here. Okay, so only the change here torque, there force in for translation systems, here torque will get, right? So these are the simple comparison table for rotational systems and electrical systems, right? So similarly same, so these are the one. So again come to the, so equivalent circuit, equivalent diagrams. So dashpot equal to the arrestor, right? So previous also you can see. Then moment of inertia J equal to the inductance, that is inductance. Then spring constant equal to the reciprocal of the capacitance, right? Reciprocal of the capacitance, right? Now coming to the torque current. So previously you are taking the torque voltage analogy. Now it is a torque current analogy, right? So here torque current. So because of the previous case it is voltage, now it is current, right? Now angular velocity, so it is voltage. Okay, here angular displacement, real charge will come, charge, right? Here dashpot, conductance will come. Then moment of inertia, capacitance, then strip constant. So 1 by, that is inverse of the inductance. Same, these same Newton's second law, Kirchhoff's current law. So current analogy, current law, like that you can keep it in mind. So previous torque voltage, then KVL came here. Now this, see the simple comparison table, mechanical systems and electrical systems, right? Now the equivalent circuits also you can see. So the dashpot same as the resistor, right? Then the spring constant, now inductance. Previous cases spring constant is equal to now capacitance. Now it is because these are two reversed, right? Now moment inertia equal to capacitor. Okay. Now the similarly the same guidelines you have to follow, whatever you see in the previous case, the same guidelines also you can follow, right? Now you can see the one simple example. Taking the two similar previous case. So I am taking P1, M2 in translation system, same as now we are taking the moment of J1, J2, right? So they only one torque, then two rotation angles, theta 1, theta 2, then spring constants, only spring constant, dash parts B1, B2, spring constant K1, K2, right? Now angular displacement J1, J2 with the theta 1, theta 2, right? Now see the free body diagram. Free body diagram for J1, right? So we are applying the torque and rotation theta 1. So remaining are the opposite, actually these are opposite direction. Printing mistake, opposite direction. So apply torque equal to the TJ1, TB1, TK1. TJ1 because it won't weight or inertia. So TB1 dashpot, TK1 spring constant. Until this is the opposite direction. Okay, opposite direction. So J1 d squared theta 1 by dt squared. Then b1 d theta by dt, then k1 to theta minus 1 minus theta 2, because k1 is between the two moment of inertia J1 and J2, between two moment of moment of inertia. That's why theta minus theta 2, right? Now look to the next case, J2. We are taking the next moment of J2. So theta 2. Okay, so these are also in opposite direction, not same direction. These two are opposite direction. They are printing mistake, right? Opposite direction. So 0 equal to the Tj2 because of one weight, then between the dash dot Tb2, then constant K1, K2. Okay, so here checking the J2 d square theta by dt square, B2 d theta 2 by dt, K2 into theta 2 plus K1 into theta minus theta equal to 0, right? Now in place of d square theta d square dw by dt, in place of d theta by dt w, now charge q equal to integral omega dt. So we have to replace the terms here. So d square theta in place of d square theta you have to write to d omega dt, in place of d theta by dt you have to write to omega, in place of q you have to write out the integral omega dt. Okay, now applying these two in first previous two equations. Okay, so t equal to now, so j1 d omega 1 by dt, because there you will get the d square theta by dt square, no d omega 1 by dt, right? So previous case b1 into d theta by dt, now theta by dt equal to nothing but omega, right? No omega 1. Okay, then q in place of constant, you have q equal to integral omega, so in place of q you are taking the integral omega dt, right? And here, so now similar thing I apply for second equation also, for this equation also same equation, right? Just replacing, so you can d square theta by dt square, you can observe it d square dt square, what you have replaced d omega dt by d omega d2 by dt. Okay, then you have taken, okay, then b2 omega dt, so you can d2 d theta 2 by d, in place of d theta 2 by dt you have to write to omega. Clear, right? Similarly in spring constant also writing that. So now replace the terms, two terms here. Now take the first one, torque voltage analogy, torque current analogy, right? So here T equal to voltage, that is EMF, J1 L1, B1 R1, K1 equal to 1 by C1, theta 1 I1, theta 2 I2. So you are taking the electrical, that is a force current analogy, right? Now apply the KVL, so L1, so this is the equation. So this is the torque voltage, you can have the torque voltage. There are how many J1 J2, so two loops I1 I2, there J1 J2, right? So x1 x2, in place of x1 x2 we are write I1 I2. Clear? So J1 J2, so J1 is 1 by C1, J2 1 by C2. Then what is the spring constant are there? Spring constant dash part, so spring constant of R1 dash part L1 L2 will come. See, so previously already was in torque voltage equivalent circuit in translate systems also same are written here. Okay, same thing, right? Similarly for torque current analogy, so torque current analogy you can observe between, so these are the two nodes, they are J1 J2, so in place J1 V1, in place J2 V2. Now how if we write here, so for these are the individual elements, now these are the common between the V1 and 2, so which is common you can observe here. See, so which is common? K1 is common. So that's why it came in the between the two nodes. This is also common here, right? Between the two nodes, this is the common. Okay, these are the individual elements. This is the common element between the V1 and V2. Clear? So these are the J1, J1. Okay, so the elements, two elements connected. You can observe here. See, K1. So B2, right? B1, right? Next K1. K1 common element, right? So like that you will get the equation, simple equation. So we can replace mechanical with electrical systems. We can replace with the translate systems to the mechanical systems, and mechanical systems translate. Okay, so we are taking mechanical systems, right, and converted to electrical systems in two cases. One is the translation system, second one is the rotational systems, right? So these are the simple example. So how to convert the mechanical systems to electrical systems. In electrical systems also there are two cases. What is the two cases are there? Current analogy, voltage analogy. Okay, so in translation analogy system we will get the force voltage, force current. In rotational analogy system we will get the torque voltage, torque current. Got right? So these are the two examples to convert there. Okay, thank you.